Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm your moderator. I'm Eve Anderson, Senior Director for Accessibility at Google. Prior to Google, I co-founded Ars Digita Corporation, an open source software company that was acquired by Red Hat, and co-authored 2 books on software development. I'm also a member of the ACM Practitioner Board and past chair of the ACM Professional Development Committee. For more on my background, check out the bio widget on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. Some of the highlights are shown on your screen. ACM recognizes the role of computing in driving the innovation that sustains competitiveness in a global environment. ACM provides access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. If you have questions at any time, please type them into the Q&A box and click Submit. I'll organize the questions as Manish speaks, and we'll try to get to as many as possible. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our tech talks. You may also open the link to the survey at any time from the resources window. Today's presentation is Human-Inspired Artificial Intelligence by Manish Gupta. Manish Gupta is the Director of Google Research India. He holds an additional appointment as Infosys Foundation Chair Professor at IIIT Bangalore. Previously, Manish has led VideoKen, a video technology startup, and the research centers for Xerox and IBM in India. As a senior manager at the IBM T.J. Watson Research Center in Yorktown Heights, New York, Manish led the team developing system software for the Blue Gene L supercomputer, work for which IBM was awarded a National Medal of Technology and Innovation by US President Barack Obama in 2009. Manish holds a PhD in computer science from the University of Illinois at Urbana-Champaign. He has co-authored about 75 papers with more than 7,000 citations in Google Scholar and has been granted 19 US patents. While at IBM, Manish received 2 Outstanding Technical Achievement Awards, an Outstanding Innovation Award, and the Lou Gerstner Team Award for Client Excellence. Manish is a Fellow of ACM and the Indian National Academy of Engineering and a recipient of a Distinguished Alumnus Award from IIT Delhi. He is also a member of the ACM India Council. Manish, without further ado, take it away.
Thanks a lot, Eve. So let me share my presentation, and I hope it's visible. So I'll be talking about human-inspired artificial intelligence, and this is all work done by my colleagues at Google Research India. with collaborators, both from academia as well as our colleagues elsewhere at Google Research in particular. So today we see AI pretty much impacting all aspects of the world, including healthcare systems, agriculture, environment, energy, and so on. And as we see this growing influence of AI, I feel it becomes extremely important for us to understand more deeply the human context where these AI solutions are being deployed. And in this talk, I'll again talk about, as we have looked at some of these human contexts, what are some of, especially in countries like India, what are some of the new challenges that we have seen arise that AI has to deal with? So in this talk, I'll primarily talk about these challenges arising in the context of data that comes from humans. I'll also talk about modeling human behavior, which becomes important in many applications. And at the end, I'll spend some time on influencing, some of our ongoing work on influencing human behavior, which is a much harder problem. I'll talk about all of these three topics in the context of two broad areas where we are applying AI solutions. One is healthcare, the other is democratizing access to information. So let's start with looking at data from humans. So I'll first introduce this topic by talking about some work that has been done by our HCI team, Human Computer Interaction Research team, led by Nitya Sambashivan. So in fact, Shivani Kapania, you see the pictures of our researchers here with collaborators from Google Research in the US. This team started looking at data because data is kind of the fundamental, in some sense, building block, right? Because you start with data, and that is when you build ML models using all of that training data. And what this team observed was that while this whole world of building these ML models, while all of that work is really glamorized, not enough value is attached to the data part, the generation and often like the annotation of data. Often that aspect gets ignored, which leads to a number of problems that they refer downstream, that they refer to as data cascades. And many of these problems are arising in very, very high stakes AI applications. So this work was presented at the CHI conference earlier this year. And in fact, they received the Best Paper Award at the conference for this work. And just to give you some more details, they started by looking at data, which underpins the models that are being built using machine learning and AI. And data labeling itself is often estimated to kind of account for some 25 to 60% of the overall operational cost of these ML projects. But this aspect is often undervalued. And in particular, there are a lot of humans who are involved in this whole endeavor. Not just the collection of data, but in many cases, when you're building models based on labeled data, the labeling of data involves a fair amount of human work. And what this team observed through various, again, through the study that they did, which involved interviewing the organizations that were generating data, to organizations that were then annotating that data, to organizations that were then taking all of that annotated data and building machine learning models. They interviewed people from each of these different kinds of organizations, and they came up with these observations about data cascades, that there were all these issues that were leading to downstream negative effects. And what are the examples of some of these cascades? So they categorize them in some of these following types that are reported in this paper. One is interacting with the physical world, brittleness. What happens is a lot of times this training data is very pristine, very kind of carefully curated, and data is cleaned up and so on before you build the models. And you apply those models to the real world, and the data in the real world tends to be much messier. And often that data could evolve, there could be drift, it could become very different from the kind of training data that you had used to build your models. So that's what we refer to as interacting with this physical brittleness. There is often also inadequate application domain expertise. You can imagine that, let's say, if you're labeling data in the healthcare domain, often you need deep expertise, right, to even diagnose what that, let's say, condition is. Let's say when you're looking at a particular X-ray of a fracture, of a bone with fracture. Sometimes there are kind of conflicting viewpoints. Sometimes there may not be adequate expertise that's applied while annotating this data. Then there are often conflicting reward systems, because sometimes the people who are collecting this data and kind of, or annotating this data, they're incentivized, for instance, sometimes for volumes of how much data, right, are they annotating or collecting, and there aren't adequate incentives for looking at the quality of data, which again leads to some of these issues. And finally, areas like poor cross-organizational documentation, that the organization, often the organization that is generating data is very different from the organization which is annotating that data, which is different from the organization that is building those models, which is different, right, from organizations or users who are using those models. And often there is poor documentation, which leads to problems down the road when it comes to like selecting the right kind of models, training these models, evaluating them, and then deploying them. And sometimes you have to either kind of restart these processes, kind of go back to the drawing board. Sometimes you have to simply abandon. So bottom line, this team observed, they argued in this paper that there's a huge need for structural change in AI research and development for us to incentivize care in data excellence, that we shouldn't be only focused on the ML modeling part, we should also be paying a lot of attention to excellence of data. And sure enough, this problem came up quite independently when our AI for Social Good team launched these projects about a year and a half ago. And in fact, almost 2 years ago, when we just started as a new research lab, and we held this workshop with various nonprofits to understand some of the problems that they were grappling with. This nonprofit, Khushi Baby, told us about this. So Khushi Baby is a nonprofit that provides a data platform for health workers in the state of Rajasthan in India, especially caring for expecting mothers and their babies. And what Khushi Baby observed was that often the data that is being collected at these various health camps by these workers tends to be noisy and error prone. I mean, they would observe things like if there are blood pressure readings, they all kind of suspiciously look normal, 120 by 80 or 110 by 70, or if there's a particular threshold for the baby's weight, let's say if it's below 2 kilograms, there's some flagging, some additional scrutiny that happens. Often, like miraculously, all these weight readings are above that threshold. So they asked us, can you apply AI to help us even identify which data is potentially suspect and which workers are prone to this lack of diligence, so that they can invest in training, in the appropriate training of these healthcare workers and incentivizing them the right way. So what Khushi Baby was doing was they were earlier using some hard rules, and what our team led by Milind Tambe who leads our AI for Social Good program, together with, again, our academic partner in this case, Arunesh Sinha from Singapore Management University. What they did was they, again, took this approach to soften these hard rules and start kind of looking at probability of non-diligence, start kind of modeling the probability of non-diligence for each auxiliary nurse midwife, this healthcare worker, guided by some of those rules, but start clustering, these ANMs based on these probability curves, and then utilizing this clustering, the natural clustering, to start predicting. So whether this healthcare worker is likely to be diligent or non-diligent. And they did some trials last year, and they did see that, yes, using these techniques, they were able to come up with reasonably accurate predictions, both like as measured by recall and precision for both classes of non-diligent and diligent workers. But what I found actually interesting is that even in very different contexts, like democratizing access to information, we face challenges of what you might call data quality, but it is now arising from a very, very different, in some sense, context, in the sense that in this case, this is not a bug, this is a feature for who people are and their background. So before describing some of those problems, let me just provide a context. So this is coming up in the context of how we are trying to democratize access to information for every person in India, where we speak a lot of different languages. So in fact, the basic problem statement we are looking at is, look, for those of us who are, let's say, in this talk, in this webinar, we are the privileged ones who understand English. So for when we are looking for any information, right, we'll just go to our favorite search engine and we will look up that information and usually have fairly rich access to information in English, usually. Things are not so great if you don't speak English, because often when you come up with queries in your language, the system may not understand you very well. And even when it understands you, the kind of quality of information that you get may not be as good. So before we come to those non-English speakers, let's start with even English speakers in India, because often it is recognized that the way English is spoken in India is very different, right, from how it is spoken, let's say, in the US or in UK by native speakers. So if we look at how, again, Google search, for instance, right, utilizes AI technologies to improve the quality of search, right? One recent technology many people may already be very familiar, which made a big difference to the quality of search, was BERT, where BERT helped you understand kind of the user intent much better, so that even if there wasn't an exact match between your search query words and kind of words appearing in documents, BERT helped you understand kind of those matches, right, at a semantic level much better, and helped you get much higher quality search results. And the way BERT itself is built as a neural model is that you take this corpus of text coming from sources like Wikipedia. So let's look at this, for instance, text, which is shown here. Obama was born in 1961 in Honolulu, Hawaii. And then you mask out certain percent, let's say of the order of 15% words, and you make this neural model predict the missing words. And again, this reminds me of this exercise, right, that I don't know how all of you learned English, but when I was learning English in school in India, our teacher would give us these kinds of exercises, fill in the blanks. And the teacher was, again, testing, right, our understanding of the nuances of English language. And of course, in addition to understanding the nuances of the language, we needed the context. And the context came from both kind of words preceding the blank as well as words that follow those blanks, right? So if you were to try and predict the word born, uh, you need that context both from earlier words, Obama was, as well as in 1961. And again, now we as humans, right, can predict fairly well, right, that the word is probably born. So BERT is able to also, again, using all of these ideas from transformers, is able to do a pretty good job uh, with predicting these words. And as a result, right, we find on a number of NLP tasks, it is leading to very significant improvements. But what I'm now arguing is that BERT is insufficient, right, when it comes to handling queries from users, even in English in India. And before I talk about the queries, let me illustrate the problem with this menu card from a restaurant, which in fact our team kind of took as inspiration for their work. So this is the appetizer menu from a restaurant in India, and it lists various kind of again food items, various dishes in English and in Hindi. And you'll notice some very interesting ways in which certain words have been spelled. Look at the 10th entry, pineapple raita. So pineapple, this is now not how any native English speaker would misspell the word pineapple, right? They would typically maybe get one letter wrong, two letters kind of deviating, right, from the original spelling. You would rarely ever see a native English speaker spell the word pineapple this way. And yet, for a native Hindi speaker, actually it makes sense because, I mean, for people who kind of are able to follow Hindi, but otherwise, let me just explain. The 10th entry in Hindi also says pineapple raita. Now, if somebody kind of maps the word pineapple to the transliteration of the word pineapple in Hindi, which is shown here, that entry in Hindi, Hindi is a very phonetically consistent language. So when you kind of map this word written, transliterated in Hindi back into English, the way you spell pineapple, even native English speakers can hopefully appreciate that phonetically, this way of writing does make a certain sense. I mean, it is literally the way kind of the word written in Hindi is now getting mapped. So this is very phonetically kind of derived, and it's not, and the way we are looking at, okay, let me just make another point. Look at the other word, appetizer. So appetizer again has this kind of phonetic way in which it has been phonetically, maybe it still makes sense, but you might say, hey, what's the deal with this letter J instead of the letter S or Z over here? And this is where, again, how a person is writing is influenced by their native language. So for a native Hindi speaker, because strictly speaking, the original Hindi language doesn't have this sound corresponding to Z. The closest sound corresponding to Z is J. And this J maps, when you're typically kind of transliterating words in Roman script, you use the letter J for that. So the way this word appetizer is spelled is again influenced by the native language of the speaker. So you might, I mean, somebody who's a native English speaker might say, look, why bother? I mean, with these kinds of weird ways in which maybe somebody in this remote restaurant, right, in some part of India is misspelling. No, it's a very commonly occurring problem because we see such variants very commonly in Google's query logs. So when somebody queries Google with this term, with this query, boys shoes, where SHUJ is the spelling, can we make Google search engine understand whether what the user really meant was shoes, boys' shoes? And likewise, I have other examples. And so this led to this project called Indophony, which was, again, the initial idea came from, the observation came from Arvind, who's our lead for this team, and I have the other members of the team. So they wanted to better understand user intent in the text queries. And then along the way, they realized that as they do that, they can also use this Indophoneme approach to do better handling of accents in our automatic speech recognition systems, right? So in fact, even early on, I was telling Arvind, while you have called it Indophoneme, it's not just for India. This concept is applicable quite broadly, right? Especially when you think about the handling different accents, right? I've had the pleasure of having friends from Spain, France, Germany, Israel, China, and so on, right? And typically, when they are speaking English, right, and when I meet a new speaker from one of these countries, I can kind of usually, right, guess that, oh, they are from this country, because again, the way they are pronouncing many of these English words, right, is often influenced by their native language. Just like, I'm sure, people, right, even if you were not to see me, if you were just to hear me talk, you could probably guess, right, that here is a speaker from India. In fact, I remember when I first went to the US, the biggest complaint I got from, I was a teaching assistant at the university, and the biggest complaint I got from the students was, oh, this guy has a very thick accent. And initially it was like a shock to me, because I was thinking, oh, all of these students, they have an American accent, right, that I have to somehow understand and deal with. And to the students, right, they all had kind of the normal accent, and I was the one, right, with the Indian accent. So this is a very common kind of a problem. So what this team did with the Indophony model is that first they kind of looked at two components. One is to model the errors that are the phoneme biases that are influenced by the native language. And I'd given this example earlier, that the sound Z corresponding to Z, in fact, is getting replaced by this sound corresponding to J. Instead of Z, you have the J sound, and which is getting spelled, right, in a different manner. And likewise, there are speakers from, let's say, the state of Bengal in India, where often, because the original language, often the sound V doesn't exist corresponding to V, often it gets replaced by the sound corresponding to V. And then the other part is this phoneme to grapheme model, where they map these phonetic patterns to various spelling variations. And so what they do is, for each word in English, they're able to synthetically generate different variants influenced by the native language of different speakers. And we found that in many cases, we are finding similar variants appearing in our query logs. So, and in fact, we have early results to show that by making our query processing systems, by making our speech systems understand these variants, we are able to improve the accuracy. Now, another aspect when you're trying to handle, again, queries from users in India is code mixing. So India is a very multilingual society. Often, let's say, I'm a native Hindi speaker, but when I'm speaking Hindi, both in conversations with my family as well as often, right, even if I'm kind of querying Google, often it is very rare for me to write something in pure Hindi or speak pure Hindi. I would typically mix up Hindi and English. So this code mixing is very common. And often, I mean, when you're typing queries, you would use transliteration. So these are very common things. And another interesting thing is that sometimes, right, when you write, let's say, a query, let's say if you write the word Sundar, as in Sundar Pichai, the CEO of Google, Sundar is also a word in many Indian languages, which means beautiful. So what they mean is not, I mean, they're not looking for that query on Sundar to be converted, to be translated into beautiful. They're looking for recognition that Sundar refers to this entity, and therefore that particular word is not to be translated. But overall, I mean, what the implications of this mix of languages that we use is the systems that we are building, they need to be multilingual to begin with. We can't think about, okay, only systems that handle English language, that handle Hindi as a language, and so on. These need to be multilingual systems to begin with. And they also, when you're doing translations and so on, you have to do them in an entity-aware manner and so on. So for multilingual learning, our team basically recognized that as you kind of start with this corpus of data from many, many Indian languages, which are often not represented in standard training data sets that NLP researchers and practitioners use, you are able to now start to get the benefits of things like transfer learning from some of the higher resource languages like Hindi to lower resource languages like Telugu and Bengali. So our team built this multilingual version of BERT with significant representation from 16 Indian languages that they called Mural. And they found that with this pre-training that they did from this corpus that used a lot of text from Indian languages, they were able to significantly improve the accuracy of many NLP tasks like named entity recognition, part of speech tagging, or question and answering on both native text as well as transliterated text. So in fact, they got significantly higher accuracy of the order of almost 28% for transliterated text. And another aspect that this team looked at is that when you are now building these models, finally, you don't want to have one model for English, another model for kind of all these Indian languages, and so on. Ideally, you would like to build a single model that is able to learn from all of these language-specific models. So they use this again concept of distillation, that you are essentially you are distilling these from these English language models, the various teacher models which are language specific, to a student model which kind of merges kind of that knowledge of all the languages, and then fine-tuning that single pre-trained student model further on the downstream NLP tasks like named entity recognition, question and answering, sentiment analysis, etc. And they did find that using this approach, which was again reported in this findings of ACL, that they are able to have the student model which is doing better, in fact, on many of these tasks than the original teacher models for these languages. Moving on, okay, I need to speed up, I realize. So we also looked at, I mean, not just kind of text as in kind of language text, sometimes it also appears visually, right, as in handwritten documents. So one important class of handwritten documents that our team started looking at was medical prescriptions. Because what happens with the healthcare system in a country like India, and this is typical for many, many other countries as well, developing nations. So in a country like India, while you have a lot of hospitals kind of which do use electronic health record systems, a lot of the care is ultimately getting delivered by these doctors in mom and pop kind of clinics, small clinics, which see very little adoption of these electronic health record systems. So there, typically, the doctor is writing the medical prescription by hand. And to convert it into electronic form, you need to really understand what they just wrote. And if you just apply standard state-of-the-art OCR and handwriting recognition kind of technologies to these documents, the accuracy levels that you get, and if you're, let's say, for instance, trying to say, oh, can you identify the medicines correctly from this prescription, the accuracy that you get, levels that you get today are horrendous. So our team started looking at this problem, and the basic hypothesis is that that by combining kind of all of this OCR and handwriting recognition technologies with NLP techniques, natural language processing, and further with medical domain understanding, you can hopefully do much better than simply kind of throwing OCR and handwriting recognition kind of solution, right, at this. So in particular, for instance, for this example, you can see that the doctor is following a certain kind of, has a certain schema in mind, right? That on this side, they're listing the body vitals. This section lists, I hope you can see the cursor where I'm kind of pointing to. The section which kind of lists the observations. There's a section where they list all the medicines, and another section where all the lab reports are kind of are mentioned. And different doctors would have different ways in which they would organize these prescriptions. So our team has been, again, attacking this problem step by step, that initially, can you do a more effective clustering of at least sections of this document about which section corresponds to what kind of data being captured, and then apply kind of OCR and handwriting recognition, right, to those sections. Very briefly, let me also mention that today India accounts for the second largest number of internet users in the world. I mean, there are various reports. One report which says India has over 800 million internet users. Some other reports say there are fewer, but roughly you can still safely say that India has as many internet users as they have more. India has more internet users than twice the population of the United States, and most of these internet users do not have the traditional computers. So these smartphones, and usually low-cost smartphones, are their only device through which they access internet. And most of these users are looking for, again, voice-based interfaces. Can they interact with the phones through voice? Can they ideally do it in their native language? And can they use their camera for not just both taking pictures as well as like pointing to the QR code to make payments, or pointing to some text that they don't understand and have the phone read out what that text means? And when you look at, again, kind of deployment of ML models in this context, I mean, there are many kind of well-known issues which get, in some sense, exacerbated for this context, right? So the well-known issues are that while this is the traditional pipeline that you collect training data, you design a network architecture, train your model, and deploy it, when you deploy it in the real world, you have to worry about kind of, are the models robust to different data distributions? And again, those issues become worse in this context, because often kind of the data from these marginalized users who are using these smartphones, low-cost smartphones, they are not very well represented in a lot of the standard data sets that are used to build these ML models, right? Even in also companies like ours. So you have to pay special attention to kind of these distribution shifts. And again, our team has been doing some work, which is, again, going to be presented at the upcoming NeurIPS. Another aspect that you have to deal with is often you have to build personalized models for these users. But personalization is often at odds with privacy. Because when you build personalized models, it is known that often you can now attack these models and recover private information about the individuals. So ideally, you would like to offer these differential privacy-based guarantees that you will not be able to uncover this private information about the individual. So again, this team has been working. So together with our collaborators from the US, Prateek kind of had this paper at ICML this year on an approach to, again, personalization using, again, collaborative, that is used in collaborative filtering algorithms, but with provable guarantees for privacy. And again, they've been doing further work, which is going to appear in NeurIPS, and some further work on applying these techniques to graph neural networks. And another issue that arises is both for privacy reasons as well as for reasons of low internet connectivity. Often you want to run these, you have to run these models on the devices, not on the cloud. And these devices, especially the low-cost smartphones, often have relatively low computational kind of capabilities. So how do you kind of build models that are still performing almost as well as models that use a lot more resources, but use a lot lower level of computational resources and memory and so on. So again, our team has been working and again, some work on low-dimensional binary codes that can be used to effectively encode classes and instances that they've shown gives you reasonably good classification accuracy as well as out-of-distribution performance on standard data sets. Again, going to be presented at the upcoming NeurIPS. And again, what our team is looking at is that you have to look at all of these three classes of challenges together when you're looking at this kind of class of users, right? The low-cost smartphone users in a country like India. So I know I should be wrapping up soon. So I'll kind of very quickly cover these two aspects, one on modeling human behavior and another on influencing human behavior. So on modeling human behavior, again, I'll use this work that was done by my colleagues Pradeep Shenoy and Soumya Chatterjee, who are researchers in our cognitive ML team. So Pradeep has this cognitive science background. So he is very interested in coming up with deep learning based models of how humans think, behave, and make decisions. And so he started with some very kind of carefully designed kind of experiment where there is public data available from cognitive science researchers like Hunt and his co-authors, where they publish data on, again, several thousand kind of data points that they collected from human subjects on a simple card game where you had to you were presented this 2x2 row of cards with many cards closed, and you had to guess which is the row with the maximum product, and you could either choose to guess or for a pre-selected row you could choose to spend some resources to open one of these closed cards before you make a guess. And what they found was that while and the way this game was designed and they showed through the data that was collected, that while we think of us humans, right, as very rational people, we often carry certain biases in how we think. So one interesting observation that they confirmed through this data was that depending on how the problem is framed, whether you say for this 2 row, find the row with the maximum product or the minimum product, which is the identical problem statement for two rows, people behave differently when they are given the problem of tell me the maximum row with the maximum product versus tell me the row with the minimum product. So that's a framing bias. And then there's this confirmation bias that if I'm now believing that row A has the maximum product, I'm more likely to, given a choice, would you like to open a card from row A, I'm more likely to select, go for that option, something that confirms the kind of belief that I already have. And the dual of that if I have, let's say, not chosen to open cards in row B, then I'm more likely to choose row A as my answer, which again is strongly confirming that kind of confirmation bias. So they built this deep learning model that in fact showed these biases both in aggregate as well as, very interestingly, even on individual subjects, which is to say that, let's say, once they've collected, let's say, 5 to 10 data points on me as a human subject, if they have already data on a large population, using these deep learning models, they're able to effectively, these models are able to effectively kind of cluster me, right? Map me as close to these maybe 50 other individuals. And by utilizing data available on how those 50 individuals behave on that particular problem statement, they are able to predict, right? So this was in a very simple toy kind of a setting. But again, I found these experiments and the fact that we are able to build these models, right, to be extremely interesting and promising. And we are now looking at, can you in more complex settings, in particular, in fact, in this, I'll jump to this setting on healthy behaviors. Can you apply some of those ideas, right, in the context of nudging people towards healthy behavior? So let me jump straight to this aspect of influencing human behavior. The problem is motivated by the fact that today, lifestyle factors account for a very significant part of the global disease burden. So over 1 billion people in the world today have hypertension, which leads to, again, adverse events like heart attack or stroke many years later. And in fact, there are simple lifestyle factors that if you were to change your lifestyle along these dimensions of physical activity, diet, ensuring that you take medication if you are prescribed that medication, let's say for hypertension, and similar, in fact, analysis often holds true for conditions like diabetes as well. And likewise, you reduce your stress, you can significantly reduce your risk factors for those adverse events. And in fact, what we are aiming to show is through a randomized controlled trial, we want to show that if you are able to kind of, and today, in fact, there are individual apps that help you kind of understand the user activity in many of these dimensions. And what we are building is this app called PALS, Personalized Automated Lifestyle Suggestions, which is, again, utilizing all of these capabilities and to, in a very personalized manner, give a certain advice to an individual that if you were to, let's say, walk for 30 minutes, or in your case, you need to cut down your salt consumption, or you need to increase your intake of fruits and vegetables, it is going to really make you much healthier. So can we, and again, the right advice, while there are common guidelines, which aspect will lead to the maximum benefit for an individual, and which aspect is something that an individual is likely to pay more attention to because I may be a person who may be more inclined to listen to advice on physical activity versus diet, because I may say, look, I really enjoy my food, so please then don't tell me to change my food habits, but I'm fine with exercising more. So different individuals may also respond in different ways. And again, and our goal is, can you ultimately automatically come up with these with these nudges? And we are very far away from that kind of nirvana where we are able to do that in an automated manner. Today, we are using templates based on this theory of planned behavior. But let me not in the interest of time, let me just stop here and leave you with these takeaways that that AI, which is built on this foundation of analyzing data. When we look at data from humans, especially in the context of countries like India and many other parts of the world, we have very interesting new problems that arise. And I've listed some of these aspects. That data excellence needs greater attention. There's a need to handle a bigger universe of data that includes this informal or what you might think of as corrupted data. But often there's a method to the madness that you can exploit. And again, modeling human behavior is hard, but again, we are making an attempt to build AI-based models to predict human behavior, initially in very, very simple settings, and then trying to make these models also apply to more complex settings. And influencing human behavior is even harder. But again, as one makes progress, right, on these objectives, there are huge opportunities for real-world impact through this work. So let me stop here and take questions. Apologize for running over.
Thank you, Manish, for this very interesting presentation. Yeah, let's get to the Q&A. So our first question goes back to the beginning of your talk when you were talking about the data cascade problems. And this question is, are more data engineering roles in companies recommended to reduce this data cascade problem? What would you recommend?
Yeah, so absolutely, there is, in fact, already a recognition, right, that even though the ML modeling part is glamorized, a typical data scientist, right, or a typical data engineer ends up often spending of the order of maybe 70 to 80% of their time, right, cleaning up the data and so on, right? So that is often known. What this work on data cascades, in fact, showed is that even before you get to that data, right, there are often serious problems, right, that many companies don't even pay adequate attention to. So it's not just a matter of having the right kind of data engineers. You need to engage on this process of data collection and data annotation from a much earlier stage. You need to engage with those organizations that are doing that work of data collection and annotation, not view that as low value, low tech menial work, but understand, right, that at a deeper level, pay more attention to issues there before you start getting to this whole job of data modeling, right? So that was at least my main takeaway, right, from the work that this team did.
Thank you. All right, let's move on to questions about the NLP portion of your talk. The first question, it has two parts. One is, how have you collected these word variants? And the second part is, are these variants collected from every state, or is the distribution a bit skewed when conditioned on state?
Right, so what we have done is we have actually, for the most part, synthetically generated these variants. But what we have done is we have validated this with, so the initial inspiration came from looking at the query logs that we have, right? So these are actual queries that various users of Google search had, and we have tried to be I mean, reasonably comprehensive in terms of including kind of data from a variety of different regions in India. But I can assure you, I'm absolutely not claiming that we have truly representative data, because we know for a fact today, right, that even the search capabilities that we provide, right, there is very varying levels of kind of accuracy, right, for queries, for being able to handle queries, right, from different regions. So we know there are going to be biases, right, in even the data, right? I mean, even when we look at the query data and we try to look at query data from all of the regions, we know there are going to be certain inherent biases in that data itself. So we have tried to be as comprehensive as we can, but we are still very conscious, right, that more work needs to be done to make ultimately things truly representative, because we believe ultimately we will get more representative data when we come out with products that truly understand user intent much better and start to have many more users, right, from different regions, which will give us more representative data.
Thank you. We have an audience member who would like to know, for Bengali variants, even this could vary for Bangladesh and West Bengal, perhaps yet another dimension of democratization, right?
That's right. So often there are a number of very interesting nuances of how kind of the same base language, right? There are different dialects of the same base language, right? So it is true for Bengali. It is, I mean, true to an even bigger degree for, let's say, Hindi, because Hindi as a, when we think about, let's say, having a system that understands Hindi, there are so many different dialects, so many different variants of Hindi, like Maithili and the way Hindi is spoken in the region in, let's say, a state of Bihar versus Haryana in India and so on, that yes, you have to be aware of all of those differences.
Yeah, makes sense. All right. Our next question is, are you using a semantic search for predicting words?
No, I mean, we are effectively, again, so again, I'm not sure what the context for this question is. So let me explain the context in which I mean. So one of the things we are doing is, so our team has created this tool that we call Line Blender. And what it does is it generates synthetically, it generates different variants of different queries. So one of the dimensions of variance is the languages that are used for code switch, that are used to express that query. So, I mean, you can start with a query in English, and you can choose to mix it up with words in Hindi. You can choose to mix it up in, let's say, another language like Tamil, and so on. Another dimension is the extent to which, the frequency with which you would use words from Hindi versus Tamil, so versus English. So it can vary that. Then we often, so in a lot of the work, what we are doing is we are synthetically creating these different variants, and then we are validating whether there's a lot of these synthetic variants make sense by actually looking at query logs from the user data that we see, and see if these really correspond to real world usage or not.
Thank you. All right, I am afraid we've run out of time for today, but I'd like to thank Manish again for his informative presentation and insightful answers to the many questions. A special thanks to each of you for taking the time to attend and participate today. This talk was recorded and will be available online in a few days at learning.acm.org. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen. On behalf of the ACM, Manish Gupta, and myself, Eve Anderson, thanks again for joining us today at the talk, and I hope you'll join us again in the future. And this concludes our talk.